Okay, yeah, thanks a lot. So thanks, Ben, again, for putting on this conference, and thanks to Meredith and all the BFI folks who helped put it together. So I am going to talk, as you can see, about multidimensional screening. And in terms of sort of motivation, I think I'll start from a situation that is a fact that is familiar to all of us, which is that multidimensional screening problems are hard, right? So even if I think about sort of the simplest canonical multidimensional screening problem where, say, you're a monopolist, you're selling two goods, say, remote clickers and water bottles, and I'm a buyer with some value for each good, and there's no complementarities, right? So these, my preferences are totally separable. Even so, the problem of finding the optimal profit maximizing mechanism for selling these is a hard problem, and it's badly behaved in lots of ways. So unlike with the case of a single good where you just want to post a price, as soon as you have two goods, you often want to use probabilistic mechanisms, right? Sell them with some probability strictly between 0 and 1. You might want to we have cases that have been studied where you optimally will use a menu of infinitely many probability price combinations. We know other strange things like you can have non-monotonicity, so the distribution of buyers' values can increase in the first-order stochastic dominant sense, and yet your optimal revenue can actually go down, and so forth. Okay, so this is a frustrating problem in a number of ways. On the other hand, multidimensional screening is important for lots of things, right? So selling goods separately is one sort of canonical example, but there are lots of others that you can think about. Say, regulating a natural monopoly, in which case you might think they have several parameters of cost. There's fixed cost and variable cost, or different marginal costs for different quantities or something. Think about Merle's type public finance models. It's very natural to have multiple dimensions of unobserved private information, things like durability and different kinds of jobs, probably not described by a single parameter, and so forth. Okay, so we would really like to have tractable multidimensional screening models, or multidimensional screening models with manageable, well-behaved solutions in order to be able to make progress in some of these kinds of applications. So what I'm going to talk about today it doesn't accomplish this completely, but I think of it as a sort of a possible first step in a new direction. So what I'm going to give you is a vanilla model, a sort of very simple model that predicts a very simple mechanism, unlike the sort of traditional model of, say, selling two goods separately. And I think of this, hopefully as being a baseline on which sort of future work on these more applied topics can build. I'll say maybe more about that at the very end. So what does the model look like? So let's think about for the moment the example where you're selling remote clickers and water bottles. Imagine you're a monopolist selling each of these, but you don't have a prior over the joint distribution of values for clickers and water bottles. Instead, you have a marginal distribution for clicker values and a marginal distribution for water bottles. And you don't know how these things are correlated. And this, I think, is a sort of reasonable approximation in many settings. If you think about a customer going to a store where there is 1,000 items being sold, they probably don't really have a joint distribution for your values for all 1,000 items. Okay, so in the face of this uncertainty, what objective will the seller use? I'll assume the seller wants to use a robust mechanism. So she wants to maximize her expected profit in the worst case over all possible joint distributions that are consistent with the marginal distributions she knows. And the result is then that no bundling or probabilistic mechanisms of any kind are useful. The best thing to do is just sell each good separately. So post a price for the clicker and post a separate price for the water bottle. Now, this result, I think, is not very surprising. It's maybe sort of the most boring result you could expect for a multidimensional screening problem. There's a very simple intuition, I think, for why this should be true, which is that the profit you get doesn't depend on what the correlation structure is, right? So you know that for selling just the clicker, $4 is the optimal price, and half the buyers are going to buy at that price. And similarly for the water bottle, and so you know that you're going to get $2 from this and $2 from this, regardless of how how they're correlated. And so we're looking at a max-min problem here. Solutions to max-min problems tend to be things that equalize your payoffs against lots of possible moves by your adversary, in this case that being nature who's designing the distribution. So it's not very surprising that this is optimum, right? Another way of saying this is you sell things separately, you know what you're getting. You don't know what you're getting by bundling, so don't. On the other hand, I don't have a proof that follows this intuition. So I find this frustrating. I hopefully will convince you that well, I don't know if I will convince you, but I'll at least be able to present suggestive evidence that there is not a trivial way of proving this statement by presenting counterexamples to some easy ways you might have tried to prove it. So the proof that I will show you, or will at least sketch, is more involved than I would like. So one sort of future hope is to have sort of more intuitive proofs of this result. The result actually is much more general than I've stated here. So I've described it just in terms of a monopolist selling multiple goods. But in fact, I can prove this for basically any finite number of additively separable quasi-linear screening problems. Right? So imagine you're a principal, you're facing an agent who has multiple dimensions or multiple components of private information, and you are choosing multiple components of allocation. And for each allocation problem, the preferences over that allocation only depend on the corresponding component of the agent's type. And so these things are additively separable. And I make a similar assumption that you know the marginal type distribution for each of these components, but you don't know how they're correlated with each other. Then the worst case is always going to be to screen separately on each of these dimensions. And I emphasize this is very general. So the individual components don't need to be sort of traditional one-dimensional screening problems with single crossing assumptions, right? So for example, you could be selling, I don't know, you could be selling 4 different goods, and you know the correlation between goods 1 and 2 and between goods 3 and 4, but you don't know how they're all jointly correlated. This would say you want to sell goods 1 and 2 by one mechanism, and you want to sell 3 and 4 by a separate mechanism. Here is the obligatory slide that nobody really likes to talk about. So just to point out, this fits into several literatures, both theoretical and it talks a bit to the IO literature on bundling, which I think is sort of the biggest applied literature that where people have been interested in related questions, but there are others. So a formal model. So hopefully this will correspond to what I just described. So the components, and I'm going to try to use the word component in preference to dimension to emphasize that these things are not what we think of as one-dimensional necessarily. So each of the components is going to be a screening problem, and this can be totally abstract, right? So a screening problem consists of a space of possible types for the agent and a space of allocations that you can choose, and a payoff that depends on the type and the allocation, and a probabilistic belief about types, right? And I guess I haven't written explicitly that the agent has quasi-linear preferences, except that's going to appear implicitly down here. And so if you were given a screening problem, what you could design as a mechanism, and I'm going to assume mechanisms are allowed to be probabilistic here. So a mechanism specifies for every type a probability distribution over allocations and a transfer that satisfies the usual IC and IR constraints. Okay, so this is vocabulary. So this is what I'm calling a screening problem. And so if you are a principal faced with a single screening problem, you want to maximize your expected profit over all such mechanisms. And now the situations I'm interested in is where you have not a single screening problem of this form, but you have these multiple components. And I'm referring to the number of components as G, thinking of goods in the monopolist application. And so there is a capital G of them. They're indexed by little g. Right? So for each, so I've got this many component problems, and I'm going to define this joint screening problem. Right? So now in the joint screening environment, you've got a type, and a type of agent specifies their type within each component, and you're allowed to pick an allocation, which specifies an allocation within each component, and the agent preferences are additively separable across the components like this. And so what is a joint screening mechanism? It specifies for every type in this product type space, it picks an allocation in the product allocation space and a transfer. And allocations are allowed to be probabilistic. Since the preferences are additively separable, I don't need to think about distributions on this whole big product space. I can think about the distribution over each component separately. Right? So effectively, a joint screening mechanism picks for every type a probabilistic allocation that is in this product space and a transfer. And it should satisfy the corresponding IC and IR constraints. And how are such mechanisms evaluated? They're going to be evaluated by this robustness criterion. So let's assume you're given a bunch of component problems. So each component problem specifies types, possible allocations, payoffs, and a prior. And as in the monopolist example I described briefly, I'm going to assume that you don't have a prior distribution over the full type space. Instead, you only know these marginals. So I'll assume that you know these marginal distributions, and you think about evaluating any possible mechanism by the worst possible joint distribution that's consistent with all of the marginals that you know. So there's that worst case criterion. So one thing that you can do is to screen separately, very generally, right? So for each component G, there exists some optimal mechanism, which is what would maximize your profit if that component were the only one that existed. Right? So let me refer to the optimal mechanism for that component using this language. It's all right. X star G for the allocation rule, T star G for the transfer rule, and R star G. You can tell that I haven't made up my mind whether to call this revenue or profit. I apologize for that. R star G for the expected profit you get in component G. So if I have those things defined for each component, then I can define a corresponding mechanism on the product type space where I just say, okay, for each component, let's offer the corresponding optimal allocation for that component of the guy's type, and just make him pay for each component separately. So altogether, he pays the sum. And straightforward, this is incentive compatible and individually rational, and no matter what the joint distribution is, the expected profit you get from this is always just the sum of the individual profits. So this is one mechanism you could use. In general, you're allowed to use lots and lots of there is a very large space of possible mechanisms, right? Because there is no assumption that the G component of the allocation has to depend only on the G component of the type. Right. So typically you would think about bundling mechanisms where several components of allocation are bundled together and the agent decides to buy or not say, yeah.
Can you give us some evaluation criterion that would make us want to do that?
Something that would make you want to bundle?
Yeah.
So for example, I'll maybe say more about this later, but say McAfee, Macmillan, and Winston have a paper that says that if you're a monopolist selling several goods, you know the distribution for each good, and you know that they're independently distributed, then you basically always want to bundle.
Okay, cool.
And you can show this by looking at the sort of first order condition. Okay, so here is the main theorem is that by this worst case criterion, the best you can always do is always this separate screening mechanism. So there's no mechanism that guarantees you a higher profit than this. So if that's the result, I'll talk maybe briefly about a couple of applications beyond the one that I started with, and then I'll try to both describe some attempted proof approaches that don't work. I can't prove that this theorem is not obvious, but I can at least suggest some reasons why I think it's not obvious. And then I can show you the proof that I know of that does work. Yeah?
Do you know if there's a sense in which R star is uniquely optimal?
Right. So I think I have a mention of that. So in the monopolist problem for generic distributions with finite support, I can show that this is uniquely optimal. I don't know exactly how much that generalizes. So the way the proof will work is to construct a particular distribution for which this mechanism is optimal, and that distribution has full support, which makes me think that this is probably optimal in general because you can't sort of modify it in silly ways by just messing with the mechanism on types that have probability 0. But I don't have a totally general theorem about that. Okay, so some possible applications. So here is the monopoly problem, just sort of translated into the notation that I've been using. So here, for the goods are indexed by G. Theta G is your type, so it's your value for good G. You can be allocated the good or not. So I've written the allocation space as just consisting of no or yes, but remember that we're allowing for probabilistic mechanisms. So in fact, a mechanism is allowed to allocate the good with any probability. And so here, the result from the single good problem is the optimum is always a single posted price. And so in the multiple good problems, the sort of robust optimum will be posted prices for each good separately. You can think about the Musa-Rosen style price discrimination problem. So you could have like an interval of possible values of either of quantity or quality, depending how you like to interpret this. And you can have the consumer be parameterized by some type theta that describes their potentially nonlinear preferences over this quantity variable. And so again, the result is going to be, so in these kinds of problems, you typically would want to offer a menu of different quantities at different prices. And so here the result is going to be if you know the marginal distribution of the theta g's for each g, but you don't know the joint distribution, the robust thing to do is offer one menu for each good separately, but don't have them interact. Okay, and then I have here sort of the first couple of these I've written assuming 0 production costs by the monopolist, but of course you can incorporate cost of production just by sort of renormalizing things. Okay, so in each of these examples, the optimal mechanism by this robustness criterion is to offer a separate menu for each good. I should have at least sort of one non-monopoly sales application, just to make things less boring. So here's another application. So think about a Merle-style tax problem, right? So you're a social planner designing a tax system. Agents vary in their ability. This is going to be kind of a stylized example, so I have to adopt particular functional forms. So I'm going to assume that agents have quasi-linear preferences over consumption here. So imagine that there's a bunch of different income-producing activities that agents can engage in, and they're parameterized by a type for each activity. And so if you produce an amount yg in activity g, then you get a disutility from that particular activity that is represented by this function of the amount that you produced in your corresponding type. And then you get to eat some amount c, so your overall utility is this. And so a mechanism would specify for each type in the population how much they produce in each activity and how much they get to eat at the end of the day, subject not to IR because you're a social planner who can you can impose your will on the whole society. Not subject to IR, but rather subject to a global resource constraint that says the total amount that people consume is at most the total amount they produce, as well as the usual IC constraint. So it turns out that if you have this constraint instead of IR and you have a Rawlsian objective, so you're trying to maximize the well-being of the person with the lowest utility, that problem is actually equivalent to the problem where you have an IR constraint and you're trying to maximize an objective that looks like total profit. So the isomorphism is worked out in detail in the paper. Basically, you can use the same tools to study this problem, and so the result is going to be, again, that if you know the distribution of each type theta g, but you don't know how these are correlated across people, then the worst case optimum, at least for this particular criterion, is going to be to separate across the different activities. So within each activity, you tax and transfer separately from all other activities. And one reason that I mention this is because there has been this recent literature in dynamic public finance where people talk about sort of plausibility of history-dependent tax systems, right? So people look at sort of dynamic Merle's models where your ability follows some stochastic process, and the optimum in these models is that you want to tax people in some way that depends on sort of their ability parameter in every past period. And people debate whether this is plausible. So one possible interpretation of this model is that each G is a separate time period, and according to this robustness criterion, this would give you a reason for taxing within each time period based only on income accrued in that time period. Okay. So I said that I would, before going to the actual proof, I would sort of try to describe some attempted proofs and why they don't work, and maybe in the process build a little bit of intuition about about the multidimensional screening problems, or about sort of how to interpret the contribution here. So I've said that the sort of best you can do by this worst case criterion is to screen on each dimension separately, and you'll get this worst case profit of R star. So the way I'm going to prove this is by constructing a particular joint distribution where you can't do better than R star. So the question is, what is this joint distribution? So one natural thing that somebody might try to do first is to have the components just be independently distributed, right? And that seems like a natural place to start, right? If you know that there's no interaction between the different components in terms of the agent's preferences, and there's no sort of informational interaction, then there should be no interaction in the resulting mechanism, right? But this approach fails. It fails quite badly. So in fact, this is not a new finding. We've known for a while. So for example, if you have a large number of goods that are values are IID, then by law of large numbers, in the limit, you basically know exactly what the buyer's value is for the bundle of all goods, and so you can extract all the surplus just by bundling all of the goods together. And you can't do that by setting a price for each good separately. So it fails in big examples. It also fails in the smallest possible example. So imagine there's two goods, and for each good you have value I have value either 1 or 2 with probability a half each. So if you're selling each good separately, you can either set a price of 1 or a price of 2. Either way, you'll make an expected profit of $1 on that good. So by selling them separately, you'll make $2. But if you bundle the two goods together and sell that bundle for a price of 3, then if my values are independent, I'll buy 3/4 of the time, and so your profit is 9/4, which is more than 2. And in fact, the independent distribution fails not only in the sort of big case and in the small case, but basically always. So this was my response to Scott's question earlier. Okay, so I think we showed that method doesn't work. The other sort of natural approach that I know how to try to construct this joint distribution is to sort of have things be have the different components of type be as much correlated as possible. Right? And one reason that you might expect this to work is if you think about the special case where all of the component problems are identical, right? So you're selling clickers and water bottles, and you know that the distribution of clicker values and the distribution of water bottle values are identical. Then a natural thing to try is restrict the buyer to lie on the diagonal, so the value for the bottle equals value for the clicker. And then this is really a one-dimensional screening problem that's equal to the component problem just multiplied by G, a number of components. So in this particular special case, this works. And you might try to generalize this by taking what's called the comonotonic distribution, which is basically the values are aligned along some increasing curve in this type space. Right? So that curve is shaped in such a way that the marginal of each value is equal to whatever the given marginal distribution is. So there is a couple of problems with this, right? So one problem with this approach is that the theorem is going to be true even when the component type spaces are not one-dimensional spaces. So then it's not really going to be clear how to try to construct this comonotonic distribution. But even in even in the monopoly sales case where each of these type spaces is a one-dimensional space, we can construct this distribution and it doesn't always work. So let me show you a counterexample. So imagine that good 1 is a clicker, and I can have value 1 or 2 for the clicker with probability a half each. And good 2 is the water bottle, and the possible values for the bottle are 2, 3, and 4 with these probabilities. So you can check that for the clicker, you could either set a price of 1 or a price of 2, and either way your expected profit is a half. And your expected profit is 1. And for good 2, you can set a price of 2 or 3 or 4, and any of those will give you expected profit of 2. Right? So if you sell the two goods separately, your expected profit is 3. Here is the co-monotonic distribution for these separate distributions. So the joint values would be 1 and 2 with probability a third, 1 and 3 with probability a sixth, and 2 and 4 with probability a half. Right? So I'll show you that there is a mechanism that earns profit of strictly more than 3 against this distribution. So here is the mechanism. You can offer the buyer either good 1 alone for a price of 1, or good 2 alone for a price of 3, or both goods bundled together for a price of 5. And if you offer this mechanism, so here are the regions of the type space where the buyer buys either just good 1 or just good 2 or both goods. And so in particular, it's incentive compatible for the lowest type to buy only good 1, the middle type to buy only good 2, and the highest type to buy both goods. Right? And when that happens, your expected profit is this. It's 10 over 3, which is more than the 3 that you get from selling separately. Okay, so just to sort of try to tie this in a little bit with our sort of usual intuition about screening problems, why is it that we're able to get more from this funny mechanism than by selling each of the goods separately in this example? So one thing to notice about this mechanism is that it is not monotone in each good. Right? So the low type and the high type of buyer are both getting good 1, but the middle type isn't. And so in a sense, we're able to extract more by separate sales because we can charge the high type of buyer a higher marginal price for good 1 than we charge to the low type of buyer, which we wouldn't be able to do if there weren't this additional good 2 that we can use in another screening instrument. So I can make this precise by arguing that if this sort of monotonicity thing doesn't bind, then actually this co-monotonic distribution does work. So, so suppose that you're a monopolist selling a bunch of goods, and for each good you know that the distribution of values satisfies the increasing virtual value condition. Then this co-monotonic distribution will work. It shows that you can't achieve higher profit than you get by just selling each good separately. And you get this totally by the usual method of just writing this as a one-dimensional screening problem, doing the integration by parts and maximizing virtual value at each point. And you won't run into trouble because the monotonicity constraint doesn't bind. And so I said I would construct a particular distribution, joint distribution, where you can't do better than by selling the goods separately. So I'll describe at least at a high level, an algorithm that does this. This is what I get in this particular example with the 2 types for good 1 and the 3 types for good 2. So these are the numbers. I don't know how to interpret this. So if I could give you a sort of verbal description of what this joint distribution is, then I would do that, and it would probably make all of us happier. So right now it's kind of in search of interpretation. Okay, so let me describe sort of how the proof of this actually works. So for most of the proof, I will focus on the finite case. So finite type spaces, finite allocation spaces. And then going from the finite case to the general case is a pretty standard approximation argument. And the way that the proof is going to work is through linear programming duality. So So you can think of a mechanism design problem optimizing profit as a linear program, and what I'll do is take the linear program for each of the component problems separately, and use the dual variables from those component problems to construct dual variables and a joint distribution in the joint problem that will have the property that you can't do better than this R star you get from separate screening. And there's a bunch of things to check, so we have to check that all of the dual variables that need to be non-negative actually are non-negative. We have to check that the probability distribution we construct is actually a probability distribution, so all of the probabilities also have to be non-negative, and it has to have the correct marginals, and so most of the work ends up being in checking these things work out. So in a little bit more detail, which constraints am I going to use in the joint problem? The joint problem has lots and lots of constraints, right? Because I've got this big product type space, and for every two types, I'm going to have an IC constraint that says this type doesn't want to pretend to be this other type. Now, I'm not going to actually use all of these constraints. I'm going to consider a relaxed problem where I think only about the possibility that the agent misreports one component of his type. So if we think about here in this picture, I've got two components. There's component 1 and component 2. And let me sort of use these blue arrows to represent the IC constraints that are binding in the separate component problem, and the red arrows for the binding IR constraints. So here in one component problem, we could have multiple binding IR constraints. That's fine because I haven't made any kind of structural assumptions about what this problem looks like. And similarly here, we could have possibly the cycles of IC constraints. So the constraints that I'll consider on the joint type space when looking at the joint problem are either sort of the horizontal IC constraints and the vertical IC constraints that correspond to the ones that we're binding in the component problems, as well as the IR constraints for the types whose IR is binding in every component. That is this guy and this guy. And intuitively, these are the constraints that are going to matter in the joint screening problem. We can guess that because these are the constraints that are binding when we use the separate sales mechanism. Okay, so let me write down explicitly what the linear programming problems look like. Right? So let's start with the component problem. Right? So here is component G. So what does a mechanism for component G look like? It specifies for every type theta G, it specifies a probabilistic allocation and a transfer for that type. Right? So let me number the possible allocations, the possible pure allocations, index them by I. Right? So there's 1,000 possible pure allocations. I runs from 1 to 1,000. Then for every type theta G, I'll write xgi for the probability that that type will get assigned allocation I. So a mechanism for component G consists of all of these numbers, and they have to satisfy a bunch of constraints. Right. So the first is the IC constraint that says that type theta G doesn't want to imitate type theta hat G. Here I've written theta Gi. I've sort of abbreviated these types as vectors. So I've written theta Gi for the payoff that this type gets from allocation number I. So that's the IC constraint. The second one is the IR constraint. The third one is the one that says the probabilities have to be non-negative, and the fourth one says for every type theta G, the probabilities have to add up to 1. Okay, so a mechanism is a bunch of numbers that satisfy these 4 linear constraints. And we write out all of these constraints, and we know by linear programming duality that there exist some multipliers on these constraints, with the multipliers on the inequality ones being non-negative, so that if I multiply each constraint by this multiplier and then I add them together, I get then all of the x variables cancel, and I get this inequality that says our expected profit can be no more than R star G, which is defined as the best profit we can get. Okay, so this is the component problem. So the joint screening problem is going to work very similarly, right? So it's also going to have a bunch of IC constraints, and I said I'm only going to focus on the ICs that are concerned with misreporting along one component. So for every type theta and each possible component h, I'm going to think about the possibility of misreporting that component as being theta hat h instead of theta h. So there is a corresponding IC constraint. Here is the IR constraint for type theta. Here is the non-negativity constraints for the allocation probabilities, and here are the adding up constraints for the allocation probabilities. So in the joint problem, a mechanism specifies for every theta, it specifies its allocation probabilities for every component of the allocation, and the transfer that theta pays subject to all of these linear inequalities. Okay. So in the component problem, we had some multipliers so that we add these things, we multiply these things by their multipliers, add them up, and we get this guy. In the joint problem, we want to find multipliers so that when we multiply each of these constraints by the multiplier, we add them up, we again get total profit is at most R star, the sum of the separate profits. Except that I have not yet defined what the probability distribution over the joint types is, right? So what I want to do is simultaneously find multipliers here and probabilities here so that these add up in the correct way. Okay, so that's the proof strategy. And once we've decided to follow this proof strategy, then the rest is basically straightforward. The algebra leads us to figure out what these things what these things have to be, and then the hard work is in checking that once we write down the formulas for them, they actually turn out to be non-negative and well-defined.
Can I ask you a question about the non-proofs? So one thing that I was maybe expecting to see when kind of the proofs you might take that don't work would look maybe a little bit different than what I saw. It would take some form like, suppose that we can construct some complement operator on joint distribution. So in particular, take some joint distribution. There's a way of kind of opposing the correlations or something like that. I'm being loose here, as I said, this is a very rough idea. And then have the potential sketch of the proof be like, take some non-separated solution. Then if that does better than the separation for some joint distribution, it must do worse for the complement of that distribution. Have you gone down that path and it doesn't lead anywhere, or is it not even well defined, or?
So that sounds like a very natural proof approach. I don't know how one would go about trying to define that operator.
I see.
Yeah, so I would love to sort of have suggestions for how to implement that, because it does seem like it certainly sort of follows the verbal intuition behind the result a lot better than this stuff. And you can if you want to have a proof that looks like that, you can by brute force sort of back it out from the joint distribution that we get from this method, although that's not a very satisfying answer. Okay, so let me describe what the multipliers in the joint screening are going to be. They're going to be basically derived from the corresponding multipliers from the component problems. So for example, for the IC constraint that says this guy doesn't want to misreport as type theta hat g in component g, the multiplier for that constraint in the joint problem will be equal to the multiplier in the corresponding component problem times some reweighting coefficient that I haven't defined yet. So for every joint type theta and for every component, for every dimension g, I'm going to define one of these coefficients in a moment. Actually, I won't define them explicitly, but I'll show how they can be determined. Okay, so this is going to be the formula for the multiplier on this IC constraint. For the IR constraint, I won't have these reweighting coefficients. So the IR constraint of theta will be just the product of the corresponding component-wise multipliers. And then for the remaining non-negativity and adding up constraints, it'll again be the corresponding constraint from the component problems times some appropriate reweighting coefficient. And what I need to do is choose these reweighting coefficients in such a way that when we multiply these things by these multipliers and add them up, all of the x variables cancel out, right? Because at the end, we want to have all the x variables disappear and just have this inequality using only the t variables. OK. So that's sort of our criterion for choosing these reweighting coefficients. And that criterion gives us a system of linear equations. Right? So we've got how many equations do we have? Well, for each one of these xg variables, I'm going to have one equation that says that that variable should cancel out when we do this summation. Right? So how many of such equations do we have altogether? We have a number of types times number of components. How many variables do we have? So how many of these gamma g of thetas do we have to choose? Well, we have one for each theta and each g. So we have this many variables. Right? So we have an exactly determined system of linear equations. Morally, this should have a unique solution. But I need not only the solution exists and is unique, I also need that it's non-negative in order for these multipliers to end up being non-negative. So I need this system of equations to be sort of reasonably well behaved. This probably quickly gets to the beyond comprehensibility, so I don't want to dwell on it too much. But basically, this system of equations does have enough structure to do this. So if I focus on any particular type theta and I look at the g equations that are associated with it, one for each component, I can write these equations in such a way that that they all have the gammas of that type on one side and the gammas of other types on the other side. And moreover, I can do in such a way that all g of these equations have identical right-hand sides. And so the left-hand sides only differ in how these different components are weighted relative to each other. And that's actually what the equations end up looking like. So here the lambdas are the multipliers on the component ICs, and the kappas are the multipliers from the component IRs. The actual formula is not important. This is what the equations look like. And so the result is that indeed this system of equations has a non-negative solution. The way that I know how to prove this is by a contraction mapping and a fixed point argument. So this step, as far as I know, is kind of mysterious. Okay, so I've chosen all of the multipliers now and made them be non-negative where they need to be. And so we get, when we add up all of these equations, that the x's cancel like they should. And so the remaining question is what happens with the t variables. Right? So remember, we wanted multiply each of these constraints by our appropriate multiplier, add them up, and we want to obtain this. And I haven't defined the pi's yet. I haven't defined, these are going to be the probability of each type in the joint type space. Right? So I will simply, I have only one way of defining them. I have to define pi of theta to be whatever coefficient I get on t of theta when I add these things up. And for this to work, I need that pi of theta to be non-negative. And it turns out very nicely that for any theta, any g, we have this equation. So pi of theta is exactly the marginal, the probability on that component theta g in the marginal distribution times the reweighting coefficient. How do we get this? Basically, we get this sort of a nice property from taking the corresponding adding up property from the component problem and then multiplying through by gamma g of theta. So this in particular shows that the probability on every type in this joint distribution that I've constructed is non-negative. So where are we? So I wanted to prove the theorem by writing each component problem as a linear program and trying to construct these multipliers on the constraints and the joint distribution so that when you add up the constraints, you get the statement that the expected profit from any mechanism is at most the R star that you get from separate screening. And that has a desired adding up property by construction. And we check that everything that needs to be non-negative is non-negative. One thing we still haven't checked is that this joint distribution I've constructed is actually a possible joint distribution. So I need to check that this pi actually has the marginal distributions that it's supposed to. And this is still another step of somewhat mysterious algebra. So here is my joint type space. Here, imagine I've got 5 possible types along this dimension and 4 along that dimension. So what I want to check is that, for example, the types the probabilities that I've placed on these 4 types add up to whatever the correct marginal for this guy along the first dimension is. Well, we have this relationship between the joint probabilities and the marginal probabilities. And so this is equivalent to checking that a certain sum of these reweighting coefficients is equal to 1. So that's what we need to show. OK, so what I'll do is for each marginal type, I'll define this zg of theta g, which is the sum of these reweighting coefficients. So I need to show that all of these zg's are equal to 1. Right, so, for example, in this picture, right, for each column, I've got a z, right? And so I've got 5 of these z variables corresponding to the first dimension, and I've got 4 of them corresponding to the second dimension. Now, it turns out that if I take a certain appropriate set of these dual equations, so I'll take a dual equation corresponding to the equation that says that the xg variables for these types cancel and are big adding up. I just add up all of those dual equations. It turns out that the terms in them that correspond to all of the IC constraints in other directions cancel out, and what I'm left with is something that's a linear relationship between the z of this marginal type and the z's of some other marginal types. So this is what the equation looks like. Now again, no need to put particular attention on the details of the equation. The point is just that it is a linear equation relating the z's of the various types. So I got a bunch of such equations in this case. So for example, for component 1, I'll get 5 such equations, 1 for each of the columns, and I also have 5 variables zg. And so this system of equations has a unique solution, and it's easy to check that in this particular case, the solution really is unique, and it has all of the zg's equal to 1, which is what we needed to show. OK. So that goes through all of the steps of showing the finite case of the theorem. So we wrote out the linear program, we constructed the multipliers and the joint distribution for the joint screening problem, showed that everything that needs to be non-negative is non-negative, and that the joint distribution is an admissible distribution. That is, it has the right marginals. And so every mechanism satisfies these constraints by construction. It's going to satisfy the sum of the constraints, which is this thing. It has the expected profit against distribution pi on the right, and on the left-hand side it has some constant. I didn't actually check what the constant was, but that turns out to be fine because we know that all of the constraints that we've used are ones that are binding for this separate screening mechanism. Right? And so the value of this constant must be whatever it is in the separate screening mechanism, which is exactly the R star, the profit from that mechanism. And so this shows that separate screening is actually optimal for this distribution. And then the last step is to go from this finite case to the continuous type case. And this basically there is no deep insight here, I don't think. I borrow a result from Madaras and Pratt on approximations. So they show that if you have any screening problem, very generally, if you move the types around by a small amount in the type space, then your optimal profit will also only change by a small amount. And their result is not trivial because the optimal mechanism in general is discontinuous, but they sort of show that you can sort of pad the optimal mechanism in a way that makes the optimal profit be continuous. So how do I apply that here? I say let's start with some given continuous distribution for each component. Let's approximate those by discrete distributions on each component. Let's apply the method that was just described to get a corresponding joint distribution on this discretized combined type space. And now let's sort of map it back to a continuous distribution that has the appropriate continuous marginals. And each of the sort of continuous to discrete and discrete to continuous steps can change our optimal profit by only a small amount. So I'll spend, I guess, most of the remaining time talking about one of the most common questions that I've been asked about this result, which is how sensitive is it? So I would like to call this a robustness check, but I've already used the word robust for another purpose, so let's call it a sensitivity check. All right, so basically the result says, if you don't know anything about how the different components, theta g, are correlated with each other, then the best you can do is just screen on each component separately. So a question is, well, does this really depend on knowing nothing? If you know a little bit about the correlation, then does that overturn the result? And the answer is, well, it depends what you mean by a little bit of information. So one sort of easy way that we could try to encode a little bit of information is to impose, say, like a single moment restriction on the joint distribution, right? So instead of saying that pi is something that has the given marginal distributions, we don't know anything else about it, I could say impose one equation on pi of this form. But unfortunately, there's lots of ways that you could write down this one moment restriction that immediately overturn the result in a trivial way, right? So I could pick some other mechanism that's not separate screening and just have my moment restrictions be that this other mechanism gives me more profit than separate screening, and then clearly the result is not true anymore. So I would like to, if I can, if I am going to write down such a such a restriction, I'd like to do it in a disciplined way. One way that I know of to do this is to sort of take the one piece of inherited wisdom in the bundling literature and sort of maybe take it more literally than really makes sense, but at least try this and see what happens. Okay, so the sort of usual wisdom is that if the values for the different goods are negatively correlated with each other, that's a situation where bundling would be optimal. This comes from sort of the early examples in this literature. So I think the first paper was by Stigler in 1963. There's another one a bit later by Adams and Yellen. They basically give a bunch of examples, and the sort of flavor of these examples is, if the buyer's values for, say, the clicker and the water bottle are perfectly negatively correlated, so that you know the sum of them and you don't know the individual ones, then of course you want to bundle, right? And so, for example, if you look at Church and Ware, which is a standard undergrad IO textbook, they say this is sort of the lesson that we've learned. So let me say maybe take this literally, which might or might not make sense, but let's do it and see what happens. So let's consider all of the possible, imagine a monopoly sales problem and restrict the joint distributions by requiring that the values for the two goods are negatively correlated. And say, in this case, is there some mechanism that guarantees us more than we could get by selling separately? Or is selling separately still the robust optimum? And it turns out there's no, as far as I can tell, there's no general analytical result. So I could do numerical experiments. So I did some small scale experiments, and the result is most of the time you still can't do better than by selling separately. Okay. Here's sort of one other way of trying to get at the sensitivity problem, which I may or may not find reasonable. So, I don't know what are sort of good ways of writing down a some moment restriction on the set of possible joint distributions, other than maybe the one that we just discussed. Another way of trying to get at this is instead of writing down a particular restriction, just sort of look at the set of all possible joint distributions for which you can't do better than separate screening, and ask, is that set small or is that set large? So, there's some big space of all possible joint distributions, and there is a subset of that space where we can't do better than separate screening, right? So these are the worst case distributions. So sort of the situation that would be least favorable for the theorem is the one that looks like this, where there's just one particular distribution where you can't do better than separate screening, and for any other distribution you can. If we were in this situation, then you'd say this, this optimality of separate screening is maybe not a very comfortable result, or you don't want to put too much credence in it. And intermediate cases that there are more than one, but still not a whole lot of these worst case distributions. If this was true, then I could at least say that there is a bunch of possible moment restrictions that we could impose. Right, so there's going to be an open set of moment restrictions that would intersect this green line. So for any such moment restriction that we can impose, it would still be true that the best, the worst case optimum is a separate screening. I mean, the most favorable situation for this result would be case C, where there's actually like a full dimensional set of these worst case distributions. So I think, see, as a result, I think this gets to the question that I think it was Alex asked earlier. So at least generically with finite type spaces in the monopoly sales problem, case C is the one that obtains. So in fact, this is not a knife edge result.
Can I ask you one more question about the simulations? Did you also, so in 970 out of 1,000 cases, the separate one maximizes max min. But since you were simulating this, you can also check how often does bundling give a higher average payoff? And is the answer most of the time? Or did you not compute that?
So let's see, what would average payoff mean now? Because in the simulations, I haven't generated a particular joint distribution, right? I'm taking the max min over joint distribution still.
Well, I guess, but given that you have a discrete type space or so, you can. This is a sufficiently small space. You could think about, say,
Just
uniform.
Okay.
Some kind of uniform distribution
over the possible joint distributions.
Over possible joint distributions. Is it the case? Just since you were saying received wisdom says this, but give a caveat, this is the sense in which giving received wisdom a little bit more of a fair chance is saying, look, in fact, on average, you might. I mean, it would be interesting if it does better.
Right. Right. I mean, so I should say the received wisdom is favorable to bundling already in the sense that separate sales is a single mechanism, whereas there are lots of ways that you could bundle the goods, right? Because you could think about all kinds of combinations of prices for the individual goods and bundle prices. But it's a reasonable thing.
You just took the simplest bundle, which is just like
just bundle the two goods and sell that bundle at the optimal price and see what happens. Yeah, that's a good suggestion. Okay, so to wrap up, what was the contribution? So it's basically a theorem and a proof, right? So the theorem says if you've got an agent who is going to be screened across several dimensions of private information, and the preferences are additively separable across these dimensions, but within each dimension they can basically be arbitrary up to some regularity assumptions. Then this worst case optimal mechanism is to screen on each dimension separately. And so I talked about a few applications, including monopoly price discrimination and dynamic taxation, and suggestions for other applications are very much welcome. And the proof involved this duality method, so I would like to have a better and more intuitive proof, maybe along the lines that Amir suggested, say. At least some simple approaches to trying to prove this don't work in general. They might work in special cases. So that's one thing I would like, and sort of the other sort of future direction that I see for this is on the agenda is to sort of try to use this as a baseline from which to study more interesting multidimensional screening problems, right? So the beginning of the talk are these sort of just talking about how lots of interesting situations involve screening along multiple dimensions. This result is maybe sort of the most boring result you could expect from a multidimensional screening model, because it says, well, we just sort of separate everything. Right? So one sort of way that I think about the methodological value here is it gives us an empty baseline, right? So this is a model in which we have sort of no interactions between the dimensions going in, and we get no interactions coming out. So that if you now had a model where there were some interactions and preferences, say complementarity between several goods, it would be natural to try to write down a model like this, which allows you to get hopefully to have ruled out all of the interactions other than the one that you're interested in, and then you can ask sort of what is the economic consequence of this particular interaction. So at this point, that's kind of a vague dream, right? I don't have any examples of results along those lines to show, but hopefully in a next iteration of this, that will be taking the place of this future work slide. And I welcome suggestions for directions to explore. All right. Thanks.